Hi, this is sixth video of the series video that I'm going to explain about quantum computing. In this video, I'm going to explain about Bernstein-Vazirani algorithm. So what is Bernstein-Vazirani algorithm? So we need to talk about the function that is concerning this Bernstein-Vazirani algorithm. Let's say we have a function f from n bit strings to 0 or 1 values that is defined as the following: f of x equals to a dot x. Here, black dot is something like an inner product of binary strings. For example, if a is a 3-bit string 011 and x is 110, then we take the corresponding bits and multiply them together, which is either 0 or 1, and take the binary sum. So 0 plus 1 equals to 1. So the value of function is always 0 or 1. So the question is, how can we find out this hidden a? So we only have a function when it put the input and know what the output is. We don't know what a is. We want to find out the string of hidden a. If we use the classical algorithm, we need to query that function at least n queries. So for example, if I want to find out the first digit a0 of the string a, then I need to query the string 000 to 1. That gives me the bit of the 0th place. So you can see how we are using these n queries here. However, Bernstein-Vazirani algorithm finds a hidden a in a single query. And this is how Bernstein-Vazirani algorithm look like. We have the oracle represented as a symbol f. At the end of the algorithm, we measure all the n input wire. So let's try to compute all the quantum states one by one. So in the beginning, we initialize the input register as 0 and the output register at cat1. And we apply the Hadamard gate every single quantum state and we get the psi1. And then let's compute the psi2. The result will be like the following. And then this f of x cat minus f of x hat cat is either plus or minus of 0 minus cat 1. So we can put the sign of minus 1 to the power of f of x outside and write this psi2 as the following. So and then in the third stage, we apply the Hadamard gate again. So the output register turns into 1 and the input register is now the Hadamard gate applied to each of the input states where the bits are represented as xi. So when you have xi either 0 or 1, the result is depending on the parity of xi, so you can write the quantum state as the following. So let's replace f of x as its definition a dot x, and I'm going to write the tensor product of n input state as tensor product of the summation of ith place, which represented as yi from 0 to 1, with the coefficient minus 1 yi times xi. So here yi and xi are bits and we're taking normal multiplication. When I combine all the tensor product of input state, I get entire quantum state range from 0 to 2 to the n minus 1, but we have a sign change depend on what yi and xi's are, and if we take this exponent all in the summation 1 to the power, then we can write that as a y dot x. So combined with a dot x originally there, what we have here is the following. We can combine a and y as a summation, so it's a coordinate y summation, so it's still n-bit string dot with x. So it's just a linear combination of all cat y state with certain coefficients. So let's think about what this coefficient should be. So this summation of x from 0 to 2 to the n minus 1 are not 0 if and only if a is equals to y. Because if a is not equals to y, then at least one bit is 1 in the a plus y. So this caused the same number of 1s and same number of minus 1 in the big summation. So what does that imply? So when we measure the input register at the end of the algorithm, all what we see is going to be exactly the n-bit string of A. For example, I ran through all this quantum algorithm and I measured the input register and I recorded the outcome as C. This C is exactly the string A that we are looking for. So in this video, we talked about Bernstein-Vazirani algorithm, and in the next video, I'm going to talk about syndrome measurement. Thank you.